Hey guys, welcome to this experimental tutorial on how to drive a DC fan or any other load connected to your MOSFET. Now in this tutorial, we have a thermistor here that is going to be controlling the threshold voltage for this fan. Now as you can see an illustration here, we have illustrated here as an open. That means the fan is not turning, the supply is connected. We've got let's say we have a plus 12 volt there. We have a plus 12 volt, but your fan is not going to be turned. Why? Because the threshold is below 4. Okay, so that means the situation is off and open. Well, it's not really open. There is a high impedance here, so there is slightly small amount of current, microamps current flowing, just to complete the circuit, so that if you probe it, if you probe a voltage across this resistor here, you're going to get a voltage, but it's going to be below 4 volt. That's why there is not a lot of current. So the FET is on the off position, okay, on the off state. But now as soon as you start applying the heat to this thermistor here, that means the resistance of a thermistor is going to decrease. That means the voltage divider between this thermistor resistance and this resistance here is going to set up a different voltage at this point. Okay, so the gate voltage is basically the voltage that is dropping across this resistor. So that is the gate voltage. So long as the voltage is below 4, the thermistor, the FET is going to remain on the off state, and we're going to have a situation of a current path broken, basically. Okay, now when your threshold voltage is reached, basically the voltage drop across this resistance is equal or greater than 4. So as soon as the voltage across the gate reach the threshold, that means V is greater or equal to 4, that means the FET is going to turn on, and we're going to get a situation of a closed circuit. So the switch will be closed, the current path will be completed, and the current will flow from here, okay, into the fan, back to the drain, and then to the source. So that's the path of the current when the FET is turned on. Okay, but now that threshold voltage here, that is must be greater or equal to 4 before this IRF turn on, is now controlled by the thermistor value here, the thermistor resistance value. So we have 2 voltage drops. So if we put a plus 12 volt here, if we put a plus 12 volt there, now depending on the value of this resistance and this one, we're going to have different voltage drop. So for instance, if 4 volt is dropping across this resistance here, you're going to have the remaining voltage dropping across this one. So but as soon as this one's resistance start decreasing, this one's voltage drop is going to start increasing. That's the situation. And when this one increases to 4 volt or higher, then the FET will turn on, and that will allow the current to flow into the fan and back to the source. So that is the situation. Okay, now let's see a small demonstrations of how this thing is working in real life. Now in this tutorial, I've hooked up a MOSFET IRF 840 with a thermistor and a resistor in series with a thermistor coupling a voltage divider to feed into the gate of the MOSFET. Now the analogy is very simple here. The thermistor is an NTC that the resistance decrease based on the temperature. Okay, so based on that, the value of the resistance will set up the voltage drop appropriate on the resistor that is between the gate and the drain, and that will set up the voltage for the threshold of the MOSFET to turn on. So I'm going to demonstrate quickly here by putting my soldering iron close to the thermistor as it's going to catch the heat, and you can see if I take the soldering iron away, the fan is going to stop. If I bring it back, it's going to run. If I keep it there, it's going to run even faster, meaning the resistance have dropped significantly lower for the voltage drop to increase and go be above the threshold voltage of the MOSFET. Okay, so that is a demonstration. Now there is a lot of theory going on around it. Now let's see how to put this circuit together. Okay, so here we have with the basics component that we need for this experiment. So if you want to follow this experiment along, you're going to need a fan, a DC fan. It could be a 5 volt or a 12 volt. So if you're using a 12 volt like this one, you must make sure your power supply is also 12 volt. If it's a 5 volt, and the power supply should also be a 5 volt. Then you're going to need a resistor. So now the value of the resistor that is going to be on the voltage divider, it's going to be decided based on the temperature that you want your fan to turn on. So we're going to talk about that later. But you're going to need a resistor in the kilo ohm range. You're also going to need a thermistor, NTC, a negative temperature coefficient. So the resistance decrease based on the value of the temperature, okay? Whether it's going up. So if the temperature is going up, the resistance is going to decrease. If the temperature is going down, the resistance is going to increase. And you're going to need a MOSFET. Basics N-channel MOSFET will do. This one here is an IRF 840. It's quite a popular one. Okay, so that's a tool you're going to need for this experiment. And of course, you're going to need a nice soldering iron to do the soldering. And you're also going to need wires to complete your experiment. Okay, so if you have all the necessary tools assembled, and obviously these probes here are for my power supply, which is an array power supply. So I've set it up for 12 volt. It's going to supply me 12 volt. Okay, so if you have all the necessary tools ready, then you can start soldering. Okay guys, I'm going to stop this tutorial here. In the next tutorial, we're going to continue on by assembling our MOSFET Thermistor Fan Controller. And we're also going to discuss how to select the appropriate resistance. As you can see here, we have a 20K resistance in this illustration here. But we're going to determine what is the temperature set for the 20K resistance. And what if you want your thermistor to turn on at 50 degrees? How do you choose then the resistance? So we're going to see how to do that in the next tutorial. So stay tuned for that. So don't forget to give this tutorial a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. I thank you. Cheers. Hey guys, welcome back to this experimental tutorial on how to drive a DC fan using a MOSFET and a thermistor. Once again guys, please don't forget to like and share and subscribe to CMTEQ channel. You are more than welcome to distribute this tutorial the way you see fit. Thank you very much. So in the previous tutorial, that was part 1, we discussed a little bit of how this circuit works, and then we did a small demonstration of how the fan operates based on the changing resistance of the thermistor. So as soon as the thermistor resistance goes down because of the heat, then we have a change in the voltage drop on the gate of the MOSFET that's causing the MOSFET to turn on because it reached its threshold voltage. And then we also cover the list of components needed to achieve this experiment. That is namely your fan, a resistor, a thermistor, and your IRF N-channel MOSFET. So in this tutorial, we're then going to continue where we left off. That is by completing the assembly of this circuit as illustrated here. And after completing the assembly, we're going to test and demonstrate it once more. And then after that, we're going to see how to select this resistance. That is the resistance between the drain and the source. That is this resistance. So if you need let's say you want this fan to turn on a 45-degree temperature, what resistance value you need to choose in order to make sure that the fan turns at 45 degrees. So we're going to see the process of selecting that resistance. So stay tuned and have fun doing the experiment. Okay, so the first thing we will do here is to identify the pin out of our MOSFET that we have here. So we know this is pin 1, 2, 3. So we know according to our MOSFET data sheet, this is a gate, the middle pin is the drain, and the last pin is the source. So we're just going to bend this pin to offset them a little to allow us to do our soldering. So the gate, I'm just going to bend it this way, and the drain, I'm going to bend it the same direction, just a little lower, and then I'm going to offset the source this way. Okay, so now we've offset our 3 pins: gate, drain, and source. So the next thing to do now is solder the thermistor, the resistor, and our wire. So first off, we take the thermistor that is going to be connected from the source into the gate to form a voltage divider with the resistor. Okay, so what we're going to do is we take the two, the thermistor and the resistor, just tie them like this. Okay, then we grab our soldering iron. We just put in a little bit of solder in here on the gate, and then a little bit of solder and a little bit of solder on the pins here. Then we're going to solder right there on the gate. So what we've done here, we've completed the voltage divider between the thermistor and the resistor and solder it into the gate. So the voltage that is going to drop across this resistor is going to be the voltage that will determine the threshold to turn on this FET. Okay, so the next thing to do here is we know that this is going to go to the ground, so we can bend this way. So we bent it this way, and we need to solder it into the source. So just a little bit of press sticks there, and that bottom pin, and that pin must be soldered into the source. Like that. Okay, so now the next thing to do here is we need to solder the fan, because we know now the fan need to come between the drain and the input power. Okay, so I'm just going to solder another piece of wire like this. So I'm gonna put some solder there, and then this piece of wire is going to be mounted this way. Okay, so now we need to put our fan between these two connections. So we can bend this way. So now that we have that wire there, we can then connect the fan. We know this is going to be where the positive supply is going to be connected, so we connect our fan like this. Okay, and so the current is going to flow through the fan and through the drain, which is a middle pin, and down to the source. So now the next thing to do, the last thing to do here is only to connect the two wires for the positive and the negative of our power supply. Okay, so I'm gonna grab two wires, the red one and the gray one. So the red wire is going to come here. That's going to be the positive terminal for our power supply. Okay, so we just tin a little there, then we can just solder like that. We just need to keep this in place on the press sticks. Then we apply the solder, and then we weld it there with our solder. Okay, so that is done. Okay, so the next thing here is then to connect the gray wire, which is going to be our minus or the ground wire, onto the source pin. So we're just going to take our solder and our soldering iron, thin the wire a little, and we connect it onto the source pin right there. Okay, so we have our good connection done. Okay, so just to recap what we've done here now, we've achieved a voltage divider connection for the thermistor and the resistance that is between the gate and the source. So then the voltage drop across the bottom resistor here is going to feed into the gate, as you can see on the schematic illustration there. And then we have the one side of the resistance that is now connected onto the source. And from the source side, we have a gray wire here that's going to be our negative wire coming from the power supply. And then this top wire is the positive wire. Then we connect our fan now between the source, the positive supply, and the drain, so that the current may then flow from the power supply onto the fan, okay, and into the drain and down to the source to return for the electrons to complete their path. Okay, so now I'm going to connect the power supply now. So I'm taking the red wire and to the positive side, and I'm taking the gray wire to the negative side. Okay, then I have my fan. So we're going to see what's going to happen here. Now, as you can see right now, the fan is not turning, the fan is off, but the circuit is connected. I've got a 12-volt power supply that is set. So here is the power supply. It's an array power supply set up at 12 volt, which is connected, and it's turned on. And there is my power supply probes that's connected to the circuit, as you can see, the red wire and the gray wire, but the circuit is not running. The fan is off, regardless of the power supply being connected, but the fan is not running. Now, the reason why the fan is not turning is simply because the threshold on the gate here haven't yet been reached. So as soon as I start applying the heat into the thermistor, the resistance will start dropping. And when the resistance start dropping, what will happen is the threshold will going to be reached and the fan is going to turn. If I keep on applying the heat, the resistance will keep on decreasing and the threshold will go even higher, and that will make the effect to turn completely on. So that is what is going on here. Now I'm going to do one thing simple here. I'm going to connect a multimeter that's going to monitor the voltage across its resistance, so that we can see what's the threshold voltage when the effect is coming on. Okay, so as you can see, guys, I've now connected my multimeter between the resistance, the bottom resistance that's connected between the gate and the source. And as you can see, the voltage is 2.7, and that is way below the 4 volt. That is a threshold for the IRF 840 MOSFET. So as soon as I start applying the heat to the thermistor, you're going to see that that voltage is going to start increasing. It's going to start increasing, and you need to see, as soon as it reaches 4 volt, you must see the movement on the fan. So here we go. We're increasing it, we're increasing it, we're increasing it, and we're increasing it. And as soon as we get to 4 volt, then the fan start turning. If I remove my heat, then the threshold drops again and it stops. And I keep it back there, and so as soon as the threshold go way above 4 volt, then the fan is fully turned on. So that is how this thing is working. But now we're not sure exactly what is the temperature that is reaching that 4 volt, and that's the kind of calculations you can do. Let's say you want your thermistor to turn on when the temperature is 50 volt. I mean, let's say you want your fan to turn on when the temperature reach 40 degrees, 60 degrees, 45 degrees, and so on and so forth. So you need to know what resistance value you're going to select there to get exactly the fan to turn on at a specified temperature. Okay, let's see how we can determine what's the resistance we need there in order to get exactly the correct temperature level where the fan need to turn on. Okay, so stay tuned so we can discuss that theory. Okay guys, I'm going to stop this tutorial here. So in the next tutorial, we're going to see how to calculate that resistance value based on a specified temperature level that you want your fan to come on, or you want your MOSFET to turn on. So stay tuned for part 3 of this tutorial, how we're going to get to the bottom of that calculation. If you like this tutorial, please give it a thumbs up and don't forget to subscribe to CMTEQ channel. That will be highly appreciated. I thank you. Stay tuned for the next tutorial. Cheers. Hey guys, welcome back to this experimental tutorial on Thermistor MOSFET Fan Controller. If you are here, I am assuming that you've watched part 1 and part 2 of this tutorial. If you have, this means you have a pretty good understanding of how this circuit operates and the various components we use to assemble this circuit, as it is very well illustrated here. In the other hand, if you haven't watched part 1 and part 2, I really recommend you to go and watch those tutorials. Find the links in the description box below so that you can see how we arrived to this point. Alright, before we move forward, I would like you to stop and do one thing. Click the like button and subscribe to CMTEQ channel, because there is value in this channel. You're going to get more tutorial like this, even better, deeper understanding of basic principles of electronics and electrical engineering. Thank you very much in advance. Okay, now we move forward. In this tutorial, we'll be focusing on the simulation and calculation on how to determine the value of this resistance here. This is a value of R1. That's the same one we have here, which is a 22K for our experiment. And this resistance actually set the point where this fan is supposed to come on. Now, let's say you want the fan to turn on at 60 degrees. So basically, if this NTC detects a 60-degree temperature, you want the fan to turn on. Not less than 60 degrees. Obviously, at over 60 degrees, the fan will be fully on. But how do you get the fan to turn exactly at 60 degrees? Now, that value, that set point is set by determining the value of R1. Now, how do you find R1? How do you get that value of R1? That's what we're going to see in this tutorial. So stay tuned. Make sure you watch all the tutorial and you don't miss anything, because this is very important. Well, as you can see, I have here a circuit that is wired in Proteus simulation, which you can download from the website. Now, as you can see, I have connected 3 voltmeters. That is this one, and this one here. So voltmeter 1 is across a thermistor, voltmeter 2 across R1, and the third one is across Q1. Okay? So as you know, in order to measure the voltage drop across a device, you have to connect a voltmeter in parallel with that device. I also have inserted into the circuit 2 ammeter. So you can see there's 1 ammeter that is between the power and the thermistor. So that's basically, because this is the power wire, so I basically cut here and inserted an ammeter at that point so I can measure the current flowing into the thermistor. At the same time, I've also inserted another current meter that is connected between the fan and the drain. So that must be this wire here. As you can see, the power is flowing like this. This is my fan connection. So at this point here, where the current is supposed to enter the drain, that's where I've placed my second ammeter so I can measure the current. Now you can quickly see that this ammeter is measuring microamps current and this one is measuring amps. So that basically means there will be more current flowing here than here. Okay, so right now when I turn on this circuit here, we can see the temperature is set obviously at 25 degrees and the fan is off. The fan is not turning. Why? Because the threshold voltage is below 4 volt. It is 2 volt, as you can see. Okay, and that is a 2 volt that is dropped across R1. And we have 10 volt that is dropping across the thermistor, NTC. This 10 volt is clearly the supply voltage minus the 2 volt that is dropping across the resistance, R1. So here, basically, we have a voltage divider circuit, which illustrates Ohm law. So we can see that the current meter that is connected in this series circuit here is reading 102 microamps of current at 25 degrees. Now by Ohm law, which is V is equal to IR, does mean the voltage by Ohm law, which is V is equal to IR, means the voltage is proportional with the value of the current and the resistance. That is the voltage across these two resistance, the thermistor resistance and R1 resistance. Now, according to this thermistor's data sheet, it says the thermistor resistance is equal to 100 kilo ohm at 25 degrees C that we've set here. That is the ambient temperature. So if the resistance is 100k and we have 100 microamps of current flowing through, that means by Ohm law, the voltage drop across it is going to be 10 volt. And that's a 9.95. We are getting there pretty close. And the same will apply to the voltage drop across R1, because you have basically the same current flowing through since it's a series circuit. And if 100 microamps of current is flowing through a 20k resistance, you're going to have 2 volt dropping across that resistance. So this is how the threshold voltage is set at the gate of this MOSFET right here, IRF 840. That is by varying the voltage drop across the thermistor, which vary by changing the value of the temperature. As you can see, if I start increasing the temperature here, that means I'm dropping the value of the resistance of the thermistor. Increasing temperature means decreasing the resistance. That means decrease in voltage and increase in this voltage across R1. As you can see, that means the threshold voltage is also increasing. And you can see clearly that current is also increasing, because basically we have the total series resistance here is decreasing. So you'll have more current that will flow through that series circuit. These are basic principles of electronics. Okay, so please guys, you have to pay attention. So in a nutshell, the value of the voltage across the thermistor, that is your V threshold, is your V supply minus the voltage drop across the thermistor. The other thing I want you guys to observe is the voltage drop across the MOSFET and the current that is flowing through. As you can see here, the conditions are like the MOSFET is still off. It's not on yet because the fan is not turning. Now, as soon as I start increasing here, observe, as the threshold voltage gets closer to 4 volt, boom, as soon as I reach 4 volt, the fan start turning. Now, I'm at 46 degrees. That means my temperature was set at 45 degrees. So this 20.05 kilo ohm means the fan will start turning at 45 degrees. And now see what's happening at the voltage drop across the FET. The voltage drop across the FET is decreasing. It's no longer 12 volt. So when the fan is off, if I decrease it again, when the fan is off, the voltage drop across it is full 12 volt, full supply voltage. And the current is 0. Why? This is exactly how a switch works. An ideal switch to that matter. An ideal switch have a full supply voltage across it when it's open, and have 0 voltage drop when the switch is closed. Now let's see, as we keep on increasing the temperature to fully turn on this fan, and we observe that the voltage drop across the MOSFET is now almost 0. It's basically less than 1 volt, and you can see the fan is fully turning on, and the current flowing through here, through the fan, is now almost 1 amp of current. That means the fan is fully turned on, and the threshold voltage is way above 4. It's now standing at 5 volt. If you keep on increasing, thus you're going to see that this voltage drop across here is only going to go down because the MOSFET is now going to be fully turned on. Now, just to demonstrate this concept of an ideal switch, how a normal switch operates, I'm going to show you quickly one demonstration here. Now, to illustrate the concept of an ideal or a perfect switch or a real life switch, I've wired this simple series circuit. I've got an LED with a resistance and a switch, and I have a current meter to measure the current that's gonna flow, and a voltmeter. Now, right now, if I turn this circuit on, you can see that the LED is not turning on. The LED is off, the switch is open, but the voltmeter is showing the full voltage, the full supply voltage across the switch. Why? Because the switch is open. That's an ideal switch. As soon as the switch is turned on, I've got 29.4 milliamps of current flowing into the circuit. The LED is on, and the voltage across the switch is now 0. Now, it's not really 0 volt because now we are measuring volt. Now, if I turn this circuit off and go into the settings here, change to measure millivolt, okay, and then run the circuit again, you'll notice that there is 0.29 millivolt that is dropping here. Now, that 0.29 millivolt means there is some power that is being wasted here. Now, you know that power is equal to V times I. So we have 29.4 milliamps of current flowing through the switch, and we got 0.29 millivolt of voltage. So you can calculate the power that is dissipating across the switch by multiplying this current times this voltage. Now, you can have a lot of bad switches. For instance, let's pause this circuit again and increase the on resistance. So the on resistance is what set up the voltage drop across the switch. So if I turn this switch on again, you can see it's 0.29 volt. Now I'm going to increase the on resistance of the switch. Let's see what will happen. So I will make it 0.6 on resistance. Then I run it again. Boom. You can see I've got 1.7 millivolt. Is very small, okay? So you can multiply the 1.77 millivolt times 29.4 milliamps. You're going to have the power that is being wasted across the switch. Now, this is still small, but if you are dealing with microamps of current and low power circuitry, this is very significant. And this is why it is very important to know your on resistance of your switch. If you have a high enough on resistance, that means your switch is not very good to run into a circuit, and that could be a bad contact switch and so forth, or a bad FET or something, or a transistor. Now, even though they say transistors, FETs, and they are good switches and so forth, but there's still going to be a voltage drop across it, and that voltage drop is going to result in power losses across the switches. So for instance, if this was a real application right here, we can see there is a 0.83 volt that is dropping across this FET here. Now, at almost 1 amp of current passing through the FET, if you have 0.83 volt dropping it, you can clearly see this is almost 1 watt that is dissipating here, because you can multiply, and that's almost 1 watt. P is equal to V times I. Now, this is very important, and this voltage drop is because of the on resistance of the MOSFET. Now, let's see what's the on resistance of this IRF. This is a simulation. On our real circuit here, we haven't been yet able to measure all of that, but if we can use multimeters and voltmeters and everywhere into the circuit, we can measure the voltage drop across it, the current crossing through it, and then from that we can deduce exactly how much power is this FET dissipating, and see how efficient is our switch. Okay, because we don't want the switch to wasting a lot of power when the switch is on. The switch must not dissipate any power when it's on. That's a characteristic of an ideal switch, but clearly we don't have a lot of ideal switch in a real world. Okay, now if we look at the data sheet of this MOSFET here, we can clearly see from the get-go we have RDS on. So that is the on resistance, the contact resistance for the switch. It says RDS on is equal to 0.85. So that basically means if you have 1 amps of current flowing through the MOSFET here, you're going to have almost 1 watt of power that's going to be burning there, just getting lost, wasted. If you have 2 amps, that's power just going to be increased. If you have 4 amps, 8 amps, and so forth, you're just going to have more power being dissipated into heat. This is why you have to mount them into heat sink to improve the efficiency so that they don't burn out. Okay, so this is going to be the end of this tutorial. I promised that we were going to do calculation, but the tutorial have gotten a bit too long. So in the final tutorial on this series, we're going to really determine what will be the resistance that we can select if we want this thing to turn on 60 degrees, 45 degrees. We already see that 20 kilo ohm turns it on at 45 degrees. What if we wanted to turn at 60 degrees? What resistance we're going to select? So that is this 20k resistor, 22k resistor we have here. So right now this one is turning it at around the same temperature there. So the next tutorial, which will be the final one, hopefully we're going to see how to calculate that resistance, and I'm going to breadboard this circuit to also use that resistance we're going to select, and hopefully we can see if it's going to turn at a higher temperature. Thank you for watching. Please stay tuned for the next tutorial. Don't forget to like this tutorial and subscribe to CMTEQ channel. That will be highly appreciated. I thank you. Till next time, cheers. Hey guys, welcome back to this tutorial on how to control a DC fan using a thermistor and an N-channel MOSFET. Now we've done so far 3 tutorials in which we have explained how this circuit operates and went through the construction of the circuit and discussed a list of components needed to have this circuit assembled. Now in this tutorial, we're mainly going to focus on how to calculate this resistance here. Now this resistance is connected, if you can see, it's connected between your gate and your source. Now that is a resistance that is setting the voltage divider with the thermistor, and that divider, that voltage is then being fed into your gate as the threshold voltage. Now if I apply my soldering iron, you can see that the fan is turning on, and the hotter the thermistor gets, the faster the fan will turn. But right now I'm not exactly sure what is the current temperature set that is threshold is reaching 4 volt and the fan is turning. Now that temperature set is influenced by the value of the resistance between the gate and the source. So in this tutorial, we're going to see how to calculate the value of this gate to source resistance in order to have an exact temperature set. Let's say we want this fan to turn on 60 degrees. Now, what value of resistance between gate to source are we going to choose to ensure that this fan indeed does turn at 60 degrees? So stay tuned. We're going to see how to go through that selection. Obviously, we're going to make use of the thermistor data sheet in order to help us with that calculations. And once again, guys, if you like this tutorial, please don't forget to give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. So let's go and see how to select this gate to source resistance for a selected temperature set point. Okay, so here we have our circuit and we have the problem statement. So now consider yourself a technician or an engineer working on a system, and you've been asked to set up a circuit that will turn this fan at 60 degrees. So now you need to go into your MOSFET datasheet, your thermistor datasheet, in order to do all the calculation necessary so that this fan here can turn on at exactly 60 degrees. So we have it as a form of a problem statement. Now, given the circuit below, comprising of 100K NTC, that's a negative temperature coefficient thermistor, and a non-resistor, which is the one that you need to calculate, and an N-channel MOSFET driving a DC fan. Now, determine the value of the unknown resistance needed to turn the fan on at 60 degrees. Okay? Now, the first thing to do here is obviously you need to look at your thermistor datasheet. Now, using the thermistor datasheet, you have to write down the value of RTH. That is the thermistor resistance that corresponds to 60 degrees. Now, because we know that these thermistor here have an internal resistance that vary according to the temperature. So, for every temperature set, there is a corresponding resistance. So, you have to look now into the datasheet and write down the corresponding resistance value for 60 degrees. So, let's go ahead and find our thermistor datasheet. Now, for 100K standard thermistor, this is the output table that I found on the internet. There's quite a lot of data sheet for these standard thermistors that you can find. As you can see, this is a typical thermistor output. As you can see, the value of the resistance will be decreasing based on the temperature. And you can see basically from 125, 150 degrees, the thermistor will have a value, an effective resistance in ohm almost of 0 ohm. And you can make a projection here. There is a value of 50. This is 5K. If we have to look at it, it's 5,000 ohms. So that is 5K is projecting at about 40 something, almost 50 degrees. But okay, we don't have to look at the graph. Let's come over here on this data table and look for 60 degrees because we want to turn our thermistor at 60 degrees. As you can see here, there is 60 degrees. Let's just make sure because they are degree C and degree Fahrenheit. Okay, these are the degree Fahrenheit and these are the degree C. So 60.5, that's roughly 60 degrees for us, and that is equivalent to 141 degree Fahrenheit. Okay, now the thermistor resistance that is equivalent to 60 degrees is 22.1 kilo ohm. That's 22,000 ohm. We know that at 60 degrees, the thermistor resistance is going to be 22.1 kilo ohm. Okay, so now that we know that information, we can then write it down. So we know that our thermistor is equal to 22.11 kilo ohm at 60 degrees. Now what we need, what we are looking for is the value of this resistance. Now we can call this resistance R1. So we need a value of this resistance that will set up a voltage divider with this 22.1 kilo ohm to give us a threshold voltage of 4 volt. So that's what we need, a value of R1 to give us the threshold voltage of 4 volt to trigger so that the thermistor, the DC fan can start turning. So this is now our circuit. So we got our thermistor and this is R1, that's a 12 volt from the supply. And this is a V threshold 4 volt that must go into the gate of the N channel MOSFET. As you can see, we've completed a voltage divider circuit. Okay, now the voltage divider formula is very simple. V threshold, okay, V threshold, so that is the value of the output voltage of the divider, is equal to the voltage drop across this resistance R1 divided by the voltage drop across R1 plus the voltage drop across R thermistor. So that is VR1 over VR1 plus VRTH times the input voltage. Now we know what is the input voltage. In this case, the input voltage is 12 volt. Now expanding our formula, we get V threshold is equal to IR1 because VR1 can be replaced by the voltage drop that is across the resistance. Okay, R1 and R thermistor. Now, as you can see in the following formula here, we've got quite a couple of unknown here. We don't know what is the current is going to be, that is I. So it's a series circuit. So the current flowing from 12 volt is the same current that is going to flow down below here. So it's a series circuit. That's the same current that's flowing. We don't know the value of R1. That's exactly what we're looking for. But we know the value of RTH and we know the in. We are also know what is V threshold. That is going to be 4 volt. So basically, we can put our problem statement. We got V threshold 4 volt. We got V in, that is 12 volt. R thermistor, that is 22.11 kilo ohm. And we're looking for R1. And we don't have I. Okay? So what we're going to do now here is to manipulate our equations. So by manipulating our equation, we then factor the I out. Okay? We factor I out. And that basically means we can cancel these I. So now we don't have to worry about I anymore. So our equation become much simpler. So we only have now V threshold is equal to R1 over R1 plus RTH times V in. Now from here, we can start working it out. So we replace the V threshold with 4 volt and R1. We don't have the value, then we replace RTH. We replace RTH, that is our thermistor with 22.11 kilo ohm, and our V in, that is equal to 12. Further transformations yield 4R1 plus 88.44 kilo ohm equal to 12R1. So what we've basically done here is we've multiplied this expression here with the 4, and R1 is already multiplying the 12. That's basically why we have this expression here. So the 4 is multiplying the R1 and the 4 is also multiplying the 22.11 kilo ohm. Then this is how we get to this expression here. And moving forward, we then can regroup the like terms. So we know that we are looking for R1. So we bring this 12 R1 on this side, and then the 88.44 kilo ohm, we shift it to the other side. And we know when the terms switch the side, it goes to the other side of the equality, so it becomes a negatives, and vice versa. So now we got 4R1 minus 12R1 is equal to minus 88.44. Okay, now we can just do these basic subtractions between the two, and so this operation yields us minus 8R1, that is equal to minus 88.44 kilo ohm. And we can multiply both sides with minus 1. So basically this minus will cancel out. So we're not going to have a negative number anymore. And that basically will mean R1 is now going to be equal to this expression divided by this 80 here. And that is 88.44 kilo ohm. Okay. Now this is going to be equal to 11.055 kilo ohm. Now, what does this mean? This means that replacing R1 here, the resistance across the gate and the source, because this is a gate, this one is a gate, and this one is a source. Okay, and the middle pin here is our drain. Now, replacing this resistance, this gate source resistance with 11.055 kilo ohm in the circuit will turn this fan on at exactly 60 degrees. Now, that is the calculation we've just done here. Okay. Now, let's prove that our calculations is indeed on spot. We haven't just wasted our time in doing this. So, let's prove this first on a simulation circuit, and then we're going to prove it on a real circuit. Okay. Now, in the previous tutorial, I've already explained how this circuit works on the simulation here. So if I run this circuit, we can see that the fan is not turning, and that basically because the threshold is below 4 volt. Now I'm going to increase the value of the temperature, and so we can see where it's turning. Okay, so now we can see that this fan is basically turning at about 46 degrees here. Okay, that's 46 degree. That's where we're getting the 4 volt and it's starting to turn. Okay, now this is based on the value of R1 being equal to 20.05 kilo ohm. Now we've just done the calculation and we found that the value of R1 must be 11.055 kilo ohm, so that the thermistor, the fan can turn on at exactly 60 degrees. So now if we replace, we just edit here, we don't have to replace it. So let's just double click and change the value here. So we calculated the value to be 11.055 kilo ohm. Now let's press OK. So now we've just changed the value of R1. Now if we now run this, we'll see that the fan is not turning. But when this value was 20 kilo ohm, this fan was turning, and look at our threshold, it's dropped. Now look at our threshold. Our threshold is sitting at 2.73 volt. It just dropped from the 4 volt. And the temperature is sitting at 47 degrees. And this 47 degree was actually turning the fan on when the value of R1 was 20 degrees. So now what needs to happen is we need to increase this. Hopefully this fan is going to turn on when we get to 60 degrees. So let's see if our calculation indeed yielded a positive result. As we can see, we're edging closer to 60 degree. Okay, at 60 degree, we're getting some movement. It's not really yet, but there is something happening if you observe, and the threshold is almost 4 volt. So if we just increase the temperature by another degree, that is 61. So marginally, the fan is turning at 61 degree. So you can clearly see that our calculations was indeed on point. Okay. So we haven't wasted our time by doing that calculation. So 11 kilo ohm is indeed turning this fan at 60 degree. But now the hotter this thing is going to get, that is the faster our fan is going to turn. And that is exactly how this circuit operates. Now this is a simulation. Now I promise that we're going to also replace this value on a real board so that we can see that the fan indeed is going to be turning at 60 degrees. Okay guys, here we are. I've managed to find the resistance value close enough to the one we calculated. We calculated 11.055 kilo ohm. Now this one here is a 12K. As you can see, it's a brown, red, orange. That is 12 kilo ohm. So when I measure it, you can see there on the multimeter we're getting 12 kilo ohm. Let me just put the multimeter right on the screen there. So the resistance value is 12K, 12 kilo ohm. So from 11.055 kilo ohm to 12K, so basically it is very much marginal. So that means our thermistor should, our fan should come on somewhere there at 59 or something, 60 degree basically, so it's not too far. So what I'm going to do here, since I already have this one here that is connected, I think it's a 22K, I'm just going to disconnect it, just cut one leg so that I can find a way to include this one into the circuit. So that's going to be a quick exercise. So I'm just going to cut right here like that. Now you see, as soon as I cut, the fan started turning at full speed. Let me bring it in. As you can see, it started turning at full speed, and that basically means we only relying on the thermistor resistance to set the threshold. There is no longer a voltage divider, so the threshold is probably way above 4 volt. I'm getting 12 volt. That is really way too much, and it can actually damage the MOSFET. So I'm going to turn it off. I'm going to turn it off, and then I'm going to connect these 12K, and we're going to see that the time it's gonna take to come on actually gonna increase a little, because now the temperature need to increase to around 60 degrees. Okay, so I've now soldered the resistance, the 12K resistance between the gate and the source. Now the previous resistance that was connected is this one here that we got one leg hanging. If I can measure it, you can see the reading there. It says 21.7 kilo ohm. So basically the temperature set point was, we can assume it was half. Okay, since we haven't done the calculation there. Now this is the one I've included. When I measure it across it, I'm reading 10.7. Now this is not the 12K, because now remember it is now connected in parallel with the gate source resistance, whatever the resistance of the gate source is for this IRF 840. So that's it's now in parallel with it. So now that's basically it. Now when I'm going to put my soldering iron to heat up this thermistor, now let me first switch it on. Switch on the voltage, so I've got 12 volt. You can see the fan is not turning. So when I apply my soldering iron, it's not turning on. It's taking a little bit of time. Now I can assure you the previous one was turning much faster. Now this one need to rise, and as soon as it rises to 60 degrees or more, then the fan start turning. And that basically what we have achieved in this tutorial by setting the temperature set point. Now we can't say for sure how much is exactly the temperature that's turning that fan on. So I'm going to look for a sensor temperature monitor that we can put close to this thermistor. Maybe we can get an approximated value of the temperature that is turning this fan on. But as of now, we can be assured that it's turning at around 60 degrees based on the calculations, because these LTC thermistors are actually very good for this kind of application. As I'm applying my heat again, it's taking time to rise to 60 degrees. As soon as it rises to 60 degrees, then the fan started turning. Okay, so that's it, guys. If you like this tutorial, please, I will appreciate a thumbs up. Hit the like button now and subscribe to CMTEQ channel. There will be more tutorial of this nature with different type of experiment in electronics. Until next time, cheers.